Hello physics students. In this video, we're going to learn about something called electrostatic potential, also sometimes referred to as potential difference, or more commonly, voltage. So out of the things that we're going to learn in this unit, this is the most abstract and can give students the most difficulty. So like for example, we learned about electrostatic force, and that was pretty intuitive that if you had a positive and negative, they attracted each other, they pulled on each other, caused accelerations. Then we took it a little bit more abstract. We learned about electric field, but even that was kind of intuitive, that a big positive charge creates a big electric field, which then creates big forces on things. This a bit more challenging. So what is voltage? Well, let me begin by showing you some examples of voltage. I've got here some batteries. As you know, you've seen these before. We've got a D-cell AA battery and then a 9-volt battery, so kind of tells you the voltage right there. Now, if I were to ask you which of these has a greater voltage of these two, most people would say this one, or a lot of people would because it's bigger. But you might be surprised to know that the voltage is the same, 1.5 volts for both of these. And then you've got this 9-volt I mentioned, and some other voltages, like when you plug a lamp in or any electrical appliance, then the socket here that you plug into has, it plugs into, in the United States, 120 volts. And another voltage that you might be kind of aware of is a car battery. So I don't have one here because it's, got acid in it, and, so I don't want to take it out of a car. But basically it'd be something about this big, and it's very heavy. You lift the car battery, I don't know, maybe it's like 40 pounds. You're like, you're lifting it up. A car battery is about 12 volts. So what I'm showing you is that there seems to be no correlation or little correlation between the voltage of a device and its size. So what exactly is voltage? Well, that's what I'm going to try and explain today. So let's begin. Potential difference, or more commonly referred to as voltage. So here's a diagram of a battery, and you see, you got this little nub on this side is flat. If you look closely at a battery, you'll see that one end is marked positive, one end is negative. So there's always two sides to every battery. This same thing, but also the 9-volt also has two terminals to it. A little out of focus here. Well, okay, so that also has two terminals, a positive side and a negative side. So, and then the car battery has typically two nubs sticking out. They're the two sides. So voltage is always two sides, including an electrical plug. If you cut one of these off, the plug would not work. The light or anything, any appliance with just one plug, it will not work when you plug that in the wall. So you need two sides, a positive and a negative. Now, later in the next topic, circuits, we will be studying batteries a lot more. And in a diagram, typically the battery is drawn not like this, but like this, a schematic. Positive and negative end, and any device, as I show, will not work unless you connect it to both sides. So must have 2 points, start and an end for voltage. Now here is the definition, the mathematical definition. Voltage, which we give a symbol V, is W over Q. The W is the symbol that we used before as work, but it can be any energy, heat, kinetic energy, potential energy. Any joule value can go in here, and you divide by the charge, you get a ratio of joules per coulomb. In other words, that is defined as a volt. Now, this formula is on the reference table in the electricity section. So, as you can see, wait for the focus, there it is right there, okay? Voltage is W over Q, okay? So, I'm going to now calculate a couple examples of voltages. As you know, Actually, I didn't create a pause yet, so let me create a pause to allow you to copy this down. Okay, so as you know, voltages create electricity, and what electricity is electrons flowing around a circuit. And this is going to kind of give us a sense of what voltage is with the next two calculations. I've got two batteries, and I'm just going to let one single electron go from one terminal of the battery to the other. And I'm going to calculate, and I'm going to say, measure the energy, the joules, for that one electron. We can't see an electron, we can't feel an electron, it's tiny. But we let it pass through the battery. In battery one, the one electron, when it goes through, it accelerates and gets a burst of energy, going from the negative to the positive terminal. And suppose that energy is 2.4 times 10 minus 19 joules. What's the voltage of that battery? I divide those two and I get 1.5 volts. And this kind of tells you why these two batteries have the same voltage even though they're different sizes. The voltage is what happens to one single electron when it passes through the battery. And basically that is a result of chemical reactions in these batteries that come from molecules. If I take one single molecule out of here that reacts and creates electricity in this battery, that one single molecule, you can't see it, you can't feel it, the voltage of that one molecule is 1.5 volts. The only reason why this one is bigger is because it has more substance and it can last longer. That's it. But each one has the same exact molecules, the same chemical reactions. Every single electron gets the same thrust going through. Both batteries only last longer because it has more stuff in it. So voltage is tiny. It's down to a single electron is 1.5 volts. Okay, you might say, oh, one electron, that's going to be a little bit, because no, it's the ratio, 1.5 volts. Now I got a second battery. I let an electron pass through that battery, and maybe it shoots through, and it gets 3.2 times 10 to the minus 16th joules. Tiny, not even a billionth, smaller than a billionth of a joule for one electron. When I do that ratio of the work per charge, I get 2,000 volts out of that battery. Again, it's only one electron. So you cannot necessarily feel this amount of energy. I get struck with this one electron in my arm. And the analogy is like in this battery, one electron kind of taps me and that ratio is 1.5 volts. This one electron slams into my arm. And when I do the joules per coulomb, I get a lot. But it's still only one electron. So I wouldn't feel that little bit of energy. It's the ratio. So I hope I'm building up this concept for you so you get a better understanding of what voltage is. Let's take a look at another example. A toaster plugged into a 120 volt outlet. That, as I mentioned, is the voltage of the outlets in the United States. In Europe, they're 220, higher voltage, but that's just, what the United States chose to run its current circuits at. So, and then let's suppose this outlet now has 1,000 coulombs pass through it. Your toaster uses a lot of charge when you plug it in. And now I want to determine the energy absorbed by the toaster from the electricity. So energy, the joules, that's the W in that equation. But before I move on, let me create a pause to allow you to copy this down. Let's move on. So we begin all calculations in Regents to starting with a formula. We plug in our voltage, 120, the charge of 1,000, the energy is the joules, the work over here. And so I just multiply the 1,000 to the other side, and now I get 120,000 joules into the toaster, and it toasts my bread nice and warm and crispy. Okay, so that is another example. But this step right here, oh, actually, before I talk about that a little bit more, let me create a pause to give you a chance to catch up if you need it. So, this step right here is critical to understanding the difference of why the toaster has so much more energy than these examples. We have the energy is the product of not just a high voltage, but how much charge goes through that voltage. And the toaster has a lot of volts, a lot of charge, and then therefore a lot of energy. But it's possible, actually, you know, I'm going to hold off on that because what I want to do is kind of show you a consequence of that concept by showing you some demonstrations I did with a Van de Graaff generator. But again, I need to send you back in time to when I did them, so time machine travel again. And what I'm going to do in the first step is I'm going to use the formula for electric field that we learned to calculate the charge that builds up on the Van de Graaff generator right before the spark happens. So I'll send you there to see the calculation, then I'll bring you back and I'll talk about it. So, ready? Here we go. All very interesting, but what I want to do is do something even more interesting. A calculation, a physics calculation. You might say, come on, that's not going to be interesting. Well, I don't know, maybe you'll find it interesting. I find it interesting. Okay, so if we know that this is the electric field that it takes for the Van de Graaff to create a spark, we could calculate the charge because we know the equation between electric field and charge. So, charge on Van de Graaff. What's the radius of the Van de Graaff generator? Well, I could get a meter stick here, and I'm seeing about 12 centimeters, 24.5 centimeters, let's just say 24 centimeters diameter, which would make a 12 centimeter, half of 24, radius. So 0.12 meters. When the charge reaches this, and it's negative because, you know, Van de Graaff's building up electrons, boom, spark. Okay, so, interesting. The amount of charge was less than a millionth of a coulomb, or about a millionth of a coulomb, okay? Now what I'm going to do is send you back in time again to that same class to show you how many volts are on the Van de Graaff right before it sparks. Now there's an equation I'm going to use in that calculation that's not part of our curriculum, the voltage of a sphere that's been charged up. So don't worry about the specifics. Don't worry about writing anything down when you're there. I just want you to see that, yes, I can calculate the voltage and make a note of the amount of volts in that Van de Graaff generator. So, here we go. Brace yourself. Back in time. Now, let's do something else. Let's calculate the voltage achieved by the Van de Graaff. Because if I know the charge and the radius, the voltage at a surface of a sphere is kq over r. At discharged, 360? No. 360,000 volts. 360,000 volts. So let me pause and give you a chance to copy this down. So quite remarkable. Let me just give you some other voltages. The wall voltage is 120. If I stick a butter knife into the outlet, everyone knows that could be fatal, right? the wires that run in a neighborhood are typically 220 volts from one conductor to the other, going from house to house. Grab those. Everyone knows you go on a telephone pole, climb, grab them, you're going to kill you. 220 is fatal. Okay? And voltages can go higher in some neighborhoods, some power lines that are like feeder power lines. 12,000 volts, also fatal. And this little Van de Graaff, 360,000 volts. Okay? Now, I'm going to reset up this Van de Graaff generator, put it back together, and I'm going to do another demonstration that might surprise you. So, give me a moment. All right, here it is. The Van de Graaff back in action. So, all right, here we go. Daredevil Tupaj. $360,000 volts. All right, so how am I not dead? 120 into the socket kills me. I just took 360,000 in my fist. And you should know the answer to this, okay? Because, remember, voltage is the ratio of the thrust per charge that a single electron gets. If I take a single electron at a zillion miles an hour, whap, hits my hand, that one electron has maybe millions of volts, and it's one electron. Okay? Is it going to kill me? I won't even feel one electron, right? So the voltage is thrust per charge. The thing that I have to worry about is not just the voltage, but the available charge. Because another equation, as we said, or the same equation, I don't know if this is in the way, but maybe I'll make some room over here. Voltage is the joules per coulomb of a charge. But if I want the joules or the energy that strikes me, I need to move these two together. So, I am getting 360,000 volts as thrust per charge on a single electron, and there's only a tiny bit of them on the Van de Graaff. So sure, they slam into my hand harder than if I put my hand in the socket. Then the electrons sort of hit my hand at a slower velocity. But here there's very little charge, so it doesn't kill me. If I put my hand in the socket, well, okay, it's only 120 volts. But it's hooked with wires all the way to the power plant. And so the charge that's delivered, the coulombs, is basically limitless for that given voltage. And then it keeps shocking me and shocking me and shocking me, and there's enough joules that builds up to cause more tissue damage. Okay, so that's why the Van de Graaff, I could take those sparks. Okay, so interesting, amazing, right? I took in my hand hundreds of 360,000 volts. Again, it was because this was high. This was a representation, hundreds of thousands, the representation of how hard each single electron strikes me. But there was only, the charge was less, or about a millionth of a coulomb. When you multiply those I got less than 1 joule in my hand. So is this a little sting, okay? Interesting. It really highlights what voltage is nicely. By the way, I could also, if I stuck this while holding it into an electrical outlet, you know, sticking it in if it had a sharp point, again, I would get 120 volts, but the charge would be nearly limitless, and that would probably be fatal. If I take this isolated, stick it into the outlet and charge it up, now it's got some electrons on it. Each one of those electrons was put there with 120 joules per coulomb. And then I touch it, I get a little zap because there were not many electrons that were stored here. Very limited charge, so the same voltage, basically no effect. Now the difficult thing about electrocution is that not only does the voltage make each electron hit you harder, but it even makes the charge flow faster. So it's like almost like a voltage squared effect in terms of the damage. If the charge is limitless, the voltage damage and danger is like voltage squared. So if the charge is limited, then really you get dangerous situations very rapidly as the voltage goes up. While you were gone, I wrote down another example that is very common, where we take the energy involved and we have to use the fact that sometimes electrons gain kinetic energy, and that goes in for W. So here's example 4. A free electron initially at rest passes through 12 volts like a car battery. Determine its kinetic energy and then its final speed. So here's the energy, the voltage formula off the reference table. We put our voltage and we put in the charge of an electron, so you might have to look that up, which is the front cover right here where my finger is in this front reference table. 1 elementary charge, which is 1.6 times 10 to the minus 19th coulombs right there. So you might have to look that up, okay? And then in a problem like this, you just multiply that over and you get the energy 1.92 times 10 to the minus 18th joules. So I'll create a pause to allow you to copy this down. The next step. So what is the speed? Now that we know the kinetic energy, we plug in KE equals 1/2 mv squared. And then we take that answer, we put that in for kinetic energy, and then the mass. I've mentioned this before. The mass of an electron is also on the front cover of the reference table right here. So as you could see, rest mass of an electron, 9.11 times 10 to the minus 31 kilograms right there. Take that, plug it in, then multiply by 2, divide by that 9, and you get V squared is this. Take the square root of both sides and you get 2,053,000 meters per second, which, by the way, is over 4 million miles per hour for one electron going to just a 12-volt battery. Really gets going very rapidly because of the small mass of the electron. So let me create a pause and give you an opportunity to copy this down. I guess I need this boxed in as the final answer. Okay, so go ahead and copy it down. Okay, so there's one more thing I want to send you back in time to see. Remember in the last video, I talked about how strong this electromagnetic force is, and particularly with just the electrostatic, the one that we learned earlier in this topic. So I have a demonstration to show you how strong, again with the Van de Graaff generator. Only a couple minutes, so brace yourself for another journey back in time. Now, another demonstration I want to do, just a couple quick things. Pipe plates, all right? Metal, aluminum pipe plates. I'll turn on the Van de Graaff generator. Spooky, haunted, right? And obviously, we know what happened. Hopefully you know what happened. This Van de Graaff became negative. Some of the negative went into the pipe plates, and then negative repel, and it lifts off the Van de Graaff generator. And here's a fascinating thing, something we really haven't talked too much about, is the strength of this electrostatic force. Because this pipe plate is pulled down through the force of gravity by an object. Planet Earth, the entire planet Earth, pulls down on this pipe plate and holds it to the top of this Van de Graaff. all of Earth. Every mountain, the Mount Everest, the Indian Ocean, Australia, Europe, all the lava inside the, or the molten core of the Earth, all that mass pulls down on this pi plate and fixes it with the force of gravity. Aligned against that, I've got one dinky Van de Graaff generator, even made of plastic and a little rubber and a thin metal. If I whack this, I could dent it. So it's not that robust at all, and yet one Van de Graaff generator against the whole Earth, and the Van de Graaff generator easily wins. And the reason why it easily wins is because it is acting through this electromagnetic force, far more powerful than gravity. I'm not talking millions, not even billions, not even trillions. There isn't even a word for how many more times powerful, mass versus charge, the electromagnetic force is compared to gravity. All right, so I hope you enjoyed that demonstration also. So today we learned about potential, sometimes called potential difference, more commonly referred to voltage. Voltage is a tiny thing that happens to just a single electron. When you do the joules per coulomb, you get a certain voltage per electron. A high voltage doesn't mean necessarily you're going to get a lot of energy to damage you if you can limit the amount of charge. But if you have a high voltage and a high charge, then that's a lot of energy. So that's kind of the concept of a thrust per electron. That's what voltage is. Now, I'm going to wrap up here, but I'm going to include another video in our Google stream that you're to watch, and it's a very fascinating video on shielding, how you can use metal to protect yourself from electricity. No one would think that. You'd think rubber, okay? But there's a very dramatic demonstration of that. First, I do something kind of dramatic. I protect the calculator from the Van de Graaff, and then you'll see something even more amazing. And I hope you enjoy that video because to me, it was just incredible, mind-blowing. All right, so I hope you enjoyed the video. I hope you got a good sense of what voltage is, and I'll see you in the next physics video.